This is your presenter Asloob Mudassar, and I am presenting slide number 79 of the course on laser physics. The question is, Fabry-Perot interferometer as described in the previous question can be used as a spectrometer. Discuss the physics of FPI as a spectrometer. The answer is, assume a monochromatic light of frequency nu incident normally on a two parallel glass plate Fabry-Perot interferometer whose separation capital L can be changed by some means. You see that in the previous topic that we have discussed in slide number 78, there we assumed a constant separation capital L or a fixed separation capital L between the two glass plates of the Fabry-Perot interferometer. But here we are assuming that the separation can be changed, but we are not mentioning the means by which it can be changed. The light transmitted through the Fabry-Perot interferometer exhibits peaks which are separated in phase by pi, that is phi is equal to n into pi, or equivalently separated in width by capital L is equal to n into lambda by 2, where n is a positive integer. That is, what is the meaning of this? The meaning is that when we get two peaks in a Fabry-Perot interferometer, the phase would differ in phi, is equal to pi, or the separation between L should satisfy this condition, that is capital L is equal to n into lambda by 2. So for n is equal to 1, the phase difference between the two peaks will be pi, and the length will be equal to lambda by 2. I would suggest that you should first have read the contents of the slide number 78 so that you can also understand these topics, because some of the formulas I am taking directly from the previous slide. If the separation capital L is changed, the peaks will shift, and when delta L becomes equal to lambda by 2, one peak will move to the position of the second peak. So you see that here I am suggesting that if you are changing the separation between the two glass plates by an amount delta L, and this delta L, if it is equal to lambda by 2, one peak will move to the position of the second peak. The separation between the consecutive peaks is regarded as a free spectral range, that is delta L with a subscript of free spectral range is equal to lambda by 2. So I shall read it as delta L FSR is equal to lambda by 2. The equivalent relationship in phase domain is computed from phi is equal to 2 pi nu over c into nr into L over cos of theta. You see that nu is the incident frequency, c is the velocity of light, nr is the refractive index between the two glass plates of the Fabry-Perot interferometer. Capital L is the fixed separation between the two glass plates, and cos of theta is the angle of refraction within the Fabry-Perot interferometer. And phi is the phase that the light will undergo when it travels from one glass plate, from the first glass plate to the second glass plate. So here we are, since we, as said earlier, that we are assuming normally incident wave. So it means that for that one we can take the value of theta is equal to 0 for normally incident wave, and we are also assuming that nr is equal to 1. That is the refractive index medium between the two glass plates is air. So assuming air as the medium between the two glass plates, then this equation is simplified, because we are now setting nr is equal to 1, and we are also setting theta is equal to 0, for which cos theta is equal to 1. So making these two changes in this formula, we get phi is equal to 2 pi into nu over c multiplied by capital L. So this is the phase that the light will encounter or undergo when it travels from glass plate 1 to the glass plate 2, when the beam is normally incident on the Fabry-Perot interferometer, and the change in phi due to if the length is if the separation between the two glass plates is changed by delta L, then of course the difference in phase that will further that will have to be endured by the light wave is delta phi is equal to 2 pi nu over c into delta L. So if the change is delta L is equal to 0, the change of phi will also be equal to 0. And if you write it as delta LC on the left hand side, you need to write delta phi c on the right hand side, where delta LC is actually the width of the peak at half maximum. So let me show you the spectrum so that you can be familiar with that one. This is the spectrum that I have shown, the first part of the spectrum. You can see that here delta C is shown over here, which is the width of a peak at its half maximum. So this is delta LC, and you can also notice that delta FSR is actually the separation between the two peaks, and it is equal to lambda by 2. And you know that here we are using only a single frequency wave, that is nu 1. Nu 1 is only the frequency that is present in the input beam. So we are getting two peaks. One is at lambda by 2. The other peaks, if we move from one peak to the other peak will be again at lambda by 2. But of course the index will change. That is from n to n plus 1. That is the separation between the two peaks is lambda by 2. So delta L FSR, that is the free spectral range in terms of distance, is equal to lambda by 2. And delta LC is the width of each peak in terms of the physical distance, and this is at the half maximum. So delta LC is also known to us. So you see that in this equation delta LC is known, and delta F and delta phi c is actually the corresponding phase value. That is, if we express this width in in the diagram, I have expressed the width of each peak in terms of the delta LC. But if you represent this one in terms of the phase, that is the width of this peak at its half maximum in terms of the phase coordinates, then that value will be represented by delta phi c. So here delta phi c is equal to 2 pi nu over c into delta LC. From the previous question, that is from the slide number 78, we have found this expression that delta phi c is equal to 1 minus square root of r1 into r2 divided by r1 r2 raised to power 1 over 4. Capital R1 and capital R2 are the power reflections of the mirror 1, of the glass plate 1 and the glass plate 2 respectively. And capital R1 is equal to small r1 square. Similarly, capital R2 is equal to small r2 square, and small r1 and r2 are the reflection coefficients of the glass plate number 1 and the glass plate number 2 respectively. These things have been explained in the previous slide. And capital F was also obtained in the previous slide, that is the fineness of the interferometer. Capital F is equal to pi into r1 r2 raised to power 1 over 4 divided by 1 minus square root of r1 and r2. And here you see that these are the power reflectivities, which are capital R1 and capital R2. So we can represent delta phi c in terms of this capital F using these two expressions, that delta phi c is equal to pi over capital F. So you see that this is actually the width of, again, delta phi c is actually the width of each individual peaks in terms of the fineness of the interferometer in phase coordinates. So we have obtained delta phi c in equation number 3, and we have also mentioned delta phi c in equation number 2 also. So from equation number 2 and equation number 3, that is equation number 2, you can see that this is equation number 2, this is equation number 3. So eliminating delta phi c from these two equations, we can get delta LC is equal to lambda by 2 into 1 over f. So this is the width of each individual peak at its half peak in terms of the fineness of the interferometer. So delta LC is equal to lambda by 2 into 1 over capital F. Now introducing delta LFSR. that is the free spectral range. Using equation number 1 we finally get, so this is equation number 1, delta L FSR is equal to lambda by 2. So introducing that in over here in this equation, that is replacing delta by 2 with the delta L FSR, we have delta LC, that is the width of each individual peak at its half maximum, is equal to the delta L FSR, that is the width in terms that is the width of the peaks in terms of that is the width of the peaks, which we call as that is the separation between the peaks, delta L FSR, free spectral range, divided by capital F is the thickness of the interferometer. So the free spectral range divided by capital F will give you then the individual width of individual peak at the half maximum of each individual peak. So delta L FSR and delta LC are clear from this diagram over here. So you can see that delta L is actually the separation between the two peaks, which we call as a free spectral range, and delta LC is the width of individual peak. The separation, the two peaks are separated in distance by lambda by 2. And here in the first diagram, that is the diagram in the top, we are using an input beam only containing single frequency nu1, and capital T is the power transmission of the interferometer, of the Fabry-Perot interferometer. Okay, so we have obtained equation number 4. This gives the width of the peaks in the spectrum obtained from the Fabry-Perot interferometer. Now we assume that the incident wave contains two frequencies nu1 and nu2, where nu1 is equal to nu and nu2 is equal to nu plus delta nu. So here we are considering two, that is our incident beam, which is incident normally on the interferometer, now contains two wavelength, two frequencies nu1 and nu2. So the relationship of phi, which is equal to 2 pi nu over c into capital L, or equivalently, because of phi, you see that phi has to differ from one peak to another peak by an integer value of pi, that is n pi is equal to 2 pi nu over c into capital L. And you see that here you can change, for example, if you change the modification, if you make the transformations, that is L is replaced by L plus delta L, then of course the nu equivalently will be replaced by nu is equal to nu plus delta nu. So making these two changes in this formula, we get n pi is equal to 2 pi into nu plus delta nu divided by c, and outside that parenthesis we have another parenthesis containing L plus capital L plus delta capital plus delta L. So delta L is actually what, that you have changed the separation between the two glass plates of the interferometer by delta L. And then you see that I have also included the two frequencies within that one, that is the nu plus delta nu. And of course the phase will be changed by integer number of multiples, because you see that every value of a phase is not possible. For the peaks to be detected, the phase has to change by an integer multiple of pi, otherwise you will not get any peak in the spectrum. So if you want to observe the peaks in the spectrum, you have to set the phase to be changed of the incident beam between the two glass plates to be equal to n pi, where n is a positive integer. So making these changes, the transformation, that is L is replaced by L plus delta L, and equivalently nu is replaced by nu plus delta nu, we have the expression to be modified as given. So n pi is equal to 2 pi multiplied by nu plus delta nu divided by c, and outside that one we have capital L plus delta L, which gives the relationship. So delta L is equal to minus delta nu over nu into L. So if you simplify this expression, you will get this relationship, that is delta L, that is the change in the width of, that is the change in the separation between the two plates of the interferometer. Delta L is equal to minus delta nu over nu into capital L, where capital L, you know, that is the separation between the two glass plates, and delta L is the change in separation. So a change in separation delta L is accompanied by a change in frequency delta nu divided by nu. This gives the separation between the two peaks, one due to nu 1 and the other due to nu 2. So this delta L actually corresponds to the separation between the two frequencies nu 1 and nu 2, and here delta nu is actually the separation between the two frequencies, that is nu 1 minus nu 2 or nu 2 minus nu 1. The two frequencies will be resolved by the spectrometer if delta L is greater than equal to delta LC, that is the separation between the two peaks due to the two frequencies nu 1 and nu 2. That separation, which is delta L, should be greater than the width of individual peaks. So let me explain with the help of this diagram. So you see that since we are assuming that our incident beam now contains two frequencies nu 1 and nu 2, and the separation between the two frequencies is delta nu. So corresponding to delta nu, when we have a change in the spectrum, in the change in the width of the change in the separation between the two glass plates of the interferometer by delta L. So you can see that this is delta L, which I have shown, and the two frequencies are nu 1 and nu 2. So the separation between the two frequencies in terms of the distance is delta L, and this delta L should be greater than delta LC. You see that if you bring the two, if the separation between the two nu 1, for example, if the separation between the two frequencies nu 1 and nu 2 is smaller, then of course these two peaks will be lying closer to each other, and the resolution will only be possible when this delta L, which is the separation between the center of the two peaks, should be at least equal to delta LC or greater than that one. Or at least the minimum requirement is that delta L should be equal to delta LC, so that you can resolve the two peaks in the spectrum, that is the peaks due to frequency nu 1 and due to the frequency nu 2. So this is the condition that we have seen in equation number 6, that the requirement is that delta L, that is the change in the separation between the two glass plates of the Fabry-Perot interferometer, should be at least greater or equal to the separation at half, that the width is greater than equal to the width of each individual peak at its half maximum, which is the delta LC. Okay, now let's come to the minimum separation between the two frequencies. So here we are assuming that delta nu m is the minimum separation between the two frequencies to be resolved. These two frequencies nu 1 and nu 2. So we are assuming, now we are setting up delta nu m is the separation between these two frequencies, such that they are resolvable by the interferometer. So delta nu m is the minimum separation between the two frequencies to be resolved. Then delta nu m over delta nu m over nu into L is equal to delta LC. That is, we have made these changes over here. So we have changed delta nu by delta nu m, and we have set delta L is equal to delta LC, because the minimum condition is that delta nu m, that is the separation between the two frequencies, should not be greater than the separation between the two consecutive peaks, between the width of the peaks. So this delta L should be a separation that should be greater than at least equal to the separation, at least equal to the width of the spectrum delta LC of the individual peaks. So what I have done is that I have made the modifications in this equation, that is, I have changed the delta nu by delta nu m, which is the minimum separation in terms of frequency between the two frequencies of the input beams nu 1 and nu 2, and delta L has been replaced by delta LC according to equation number 6, which is the minimum condition for the resolution of the two frequencies nu 1 and nu 2 represented by delta nu m. So we have delta nu m over nu is equal to L into delta LC. So, but delta LC has been found to be equal to delta L free spectral range divided by capital F, and this delta L FSR is equal to lambda by 2 as from the equation number 1. So we have replaced the value of delta L FSR is equal to lambda by 2, and then we have separated 1 over F separated from the lambda by 2. So this is the expression. Now we can write this expression, that is, we can write the left hand side and the rightmost side of this expression. So we have delta nu m over nu into L is equal to lambda over 2f over here. So we can now solve this for delta nu m. So delta nu m is equal to nu by 2 into lambda over capital L into 1 over capital F. And here we can write nu lambda is equal to C. So we have delta nu is equal to C over 2L into 1 over F. Now this C over 2L has been found to be equal to delta nu FSR. That is delta nu, that is the free spectral range in terms of the frequency. You see that if you represent this free spectral range in terms of the frequency coordinate, then delta L FSR should be written as delta nu FSR, and this is delta nu FSR as given in equation number 7. That is delta nu FSR as found from slide number 78. We derived that delta nu FSR is equal to C over 2L. So replacing C over 2L by delta nu FSR, we have the relationship that delta nu m, that is the minimum separation between the two frequencies to be resolved, is given by delta nu FSR, that is the free spectral range in terms of the frequency coordinate divided by the finesse of the interferometer. So you see that this is the condition. Now look at this condition, that is delta nu m is equal to C over 2L into 1 over F. So this is, you see that the condition that gives us that how that the two minimum wavelengths to be resolved must satisfy this condition. Now if you want to improve the resolution, that is, if the two wavelengths, if the two frequencies are close to each other, you see that if you increase the value of L, what will happen? This delta nu m will decrease. It means that the instrument will give you better resolution. So if you have a greater separation between the two plates of the interferometer, then delta nu m is further reduced, which means that you can even resolve the two frequencies which are even closer to each other. So from this equation you can find out the separation, that the condition that delta nu m is resolvable. So changing the changing the width of the interferometers, capital L by delta L, you can set the values of delta nu to be accordingly. So as said, according to this equation, that increasing, that if the separation between the two glass plates of the interferometer is increased, then delta nu m is decreased. It means that the resolution of the interferometer improved, that is, you can still resolve the two frequencies which are lying close to each other, that is, the peaks are separable. And this is the relation, that is delta nu m in terms of the free spectral range, and the free spectral range here has been represented in terms of the frequency coordinates. So this expression is only in terms of the frequency. So delta nu m is equal to delta nu FSR over capital F. Now you see that in this figure, that is in the bottom of this figure, this is the figure when the frequency, the top one is when there is only a one single frequency contained in the input beam. Now here there are two frequencies contained in the input beam, that is nu 1 and nu 2. And we have shown the separation between the two frequencies in terms of the distance coordinate delta L. So if you change the separation delta L, then of course you can resolve the two frequencies nu1 and nu2, and the condition we have also imposed that this delta L should be at least equal to delta LC. This is what we have already discussed. So let's see the caption of this figure. Plot of a power transmission capital T through the Fabry-Perot interferometer versus the frequency between the on the horizontal axis, the distance L on the horizontal axis for frequency of the incident wave containing nu1 top case, and incident wave containing two frequencies nu1 and nu2 is the bottom case. So you see that this is what we have expressed, and we have also given the conditions under which nu1 and nu2 can be resolved, and we have also discussed the condition, the minimum value of between the nu1 and nu2, which we represented as delta nu m. So what are the conditions under which delta nu m can be resolved, and under what conditions delta nu m can be improved? That is, the resolution of the interferometer can be improved so that you can resolve the two closely lying frequencies. This is what we have discussed in the topic. The ratio of the free spectral range in the frequency domain to the finesse of the interferometer, that is this relationship as given in equation number 7. So the ratio of the free spectral range in frequency domain to the finesse of the instrument determines the minimum spectral separation between the two input frequencies to be resolved by the spectrometer. Necessary parameters of the problem are explained with the help of the spectrum shown in figure 79.1, that is in this figure. So we have explained all the mathematics in this presentation, and we have also explained the figure, and we have also mentioned that the relationship between the two closely lying frequencies, how they are resolvable, and what are the mathematical expressions for the resolution of the delta nu m, and how we can improve the resolution of the Fabry-Perot interferometer, which means that how the two closely lying frequencies nu1 and nu2 can be resolvable. So this is the end of slide number 79.